Thanks for this introduction, and thanks everyone for being here, especially after the lunch break. I know it's challenging. I hope to get your attention. So I'll be talking about, let me first check the pointer. Okay, it works. I'll be going to talk about zero-knowledge proofs and their applications to blockchain, and I'll specifically focus on security risks and talk a bit about auditing experience. First, a few words about OpenZeppelin. So it's founded in 2015. It's a world leader in securing blockchain smart contracts. And it's famous for its open source contract libraries, for its Defender development platform, and also for securing many high-profile projects such as Coinbase, Ethereum Foundation, Compound, and many others. And I am part of the ZKP practice, and we specialize on reviewing and auditing ZKP components, so cryptography components and ZKP specifically. We've performed successful audits on Plonk Prover and Verifier, on Plonk Verifier, and on the latest release of the OpenZeppelin contracts library. I briefly give a bit of motivation why ZKP in blockchain, and I will introduce the main concept of zero-knowledge proofs. Then I give some applications of blockchain. You've heard about them already in previous talks. And then I will focus a bit on vulnerabilities, and I will highlight some vulnerabilities found in audits. So blockchain, as useful as it is, it has some limitations, specifically scalability and privacy. And because of its limited transaction throughput, we observe high transaction fees as the transaction demand increases. And then on the privacy side, we all know it's a transparent, immutable ledger, which is good, it's a feature. But at the same time, it presents privacy issues because transactions can be traced since the information is publicly available. And zero-knowledge proofs can help alleviate those two limitations and more than that. So informally, what's a zero-knowledge proof? In fact, zero-knowledge proofs as a concept in cryptography, they are a very old concept. So their initial proposal dates from the 80s in this seminal paper from 85. And since then, the area has been very active. And we've seen a lot of research papers from these years. But only recently, they have achieved widespread adoption and practical applications to a large extent because of blockchain. And informally, it's a protocol in which a prover proves to a verifier knowledge of some fact without revealing any information about the fact except that it exists. So what kind of facts, what kind of statements can we prove? Broadly speaking, we can prove any computational relation that can be verified efficiently in polynomial time, you can think of. And for example, a prover can prove knowledge of a preimage of a hash without revealing the preimage. So only the hash is given, and then the prover convinces the verifier that he knows a valid preimage for it. Or for example, he can prove knowledge of a discrete logarithm of a field element y. Or more closer to what we are all concerned here is in a blockchain scenario with a ZKP, we can prove, for example, that the blockchain correctly transitions from the current state root of the chain to the new state root. And when I say state root, I mean in the context of Merkle trees that reflect the chain state. So a bit more formally, it's a protocol where a prover convinces a verifier that they know a witness W for a statement X that is a member of a language L. And this language is composed of all witness statement pairs that corresponds to an NP relation R without revealing anything about W, the witness W. So the witness W is the secret part that is not revealed to the verifier, and the statement is known both to prover and verifier. And just to give an example, to give you some sense behind those concepts, like witness, statement, language, and relation, we use an example of proof of knowledge of discrete logarithms. So the prover wants to convince the verifier that he knows the value X, such that X is the discrete logarithm of the element Y. So essentially, X and Y are related by this relation. And in that setting, the witness is X, the statement is Y, so the witness is the secret value X, the statement is Y, they are related by this relation, and then the NP relation we're talking about is the set of all witness statement pairs, so basically all the X and Ys, and the language that we work over is all the elements in the field that have a discrete logarithm. Okay, enough of technical content, so let's go back a bit to more practical scenarios. Maybe one more concept to introduce. So we define zero knowledge as protocols. So this implies some kind of interaction. So there are some messages exchanged between provers and verifiers. And indeed, on the top left side, you can see a high-level description of a ZKP protocol, so an exchange of messages between prover and verifier. And then a prover sends a commitment, so some value to which he commits. In this example, it's a polynomial. Then the verifier sends a challenge, which is a randomly drawn element from the field. And finally, the prover evaluates his polynomial on the challenge and provides a proof in the form of this evaluation. So it's a very high-level description, but conveys the main idea behind zero-knowledge proofs. But the point of this slide is that zero-knowledge proofs don't have to be interactive. And that's where the Fiat-Shamir transform comes into place. And it's a tool for turning an interactive protocol into a non-interactive. So on the right-hand side, you can see an equivalent representation of a ZKP protocol that is non-interactive. And the trick is the use of a hash function. So instead of the verifier being forced to produce some random challenges, and keep in mind that in real-world protocols, we will have many more challenges than just single ones. So there will be many rounds of the protocol. So instead of generating this challenge uniformly at random, the prover and the verifier will be computing it using a hash function independently on both sides. And this hash function will be hashing public parameters, so anything that is public in the protocol, like for example, the generator of the group or the modulus of the field, plus all the messages that have been exchanged before that. So they hash all this public information and they produce a challenge C. So the benefit is that C is still pseudo-random, and that's what we require in the protocol, but at the same time it can be computed independently on both sides. And that's why interaction is removed. So you can see the protocol is turned only into a single round in which basically the prover sends his proof, which is verified independently by the verifier. And that's the situation that we see in blockchain applications. So we just send the proof that is verified. That's why the Fiat-Shamir transform is instrumental in those cases. And as we will see later, it's also the source of a lot of vulnerabilities. A few words on the fundamental properties of ZKP. So completeness, soundness, and zero knowledge. Completeness is about the fact that if a statement is true, then the verifier can be convinced of its validity with probability 1. Now, if a statement is false, that's about the soundness property, then the prover still has some negligible probability of convincing the verifier of the validity of the false proof. So the trick is the word negligible. So the probability is negligibly small. So in practice, we don't expect this to happen. And finally, zero knowledge models the fact that the statement, in the process of the proof, we don't reveal anything about the statement except the fact that it's true. Okay, and finally, we have the succinctness property. So technically, it's not a fundamental property of ZKP, but in fact, it's critical for the use of ZKPs in blockchain context. So the succinctness property states that the proof should be short. And what do we mean by short? We mean logarithmic in the size of the statement. So in other words, it is more efficient to just verify the proof rather than computing the computation yourself. And that's the critical property because of which we're using ZKPs in layer 2, for example, for addressing scalability. And we'll see how in a moment. Two examples on the two limitations of blockchain that I started with scalability and privacy. So the first one is on scaling Ethereum with ZK proofs. ZK Rollups, layer 2 ZK Rollups, these are layer 2 chains that are executing transactions off-chain. So instead of publishing all transactions on layer 1 and then executing and validating them by all the nodes, what happens is on layer 2, we execute a list of transactions that are batched together in a compressed form. But after they're executed, they're modifying the Merkle tree of the chain in some form. And as a result, the state root of this Merkle tree that reflects the current state of the chain is modified. So this is the root before the transactions have been executed, and this is the root after the transactions have been executed, but on layer 2. So far we have no validation, we have no trust that transactions are valid. So instead of executing all those transactions on layer 1, we are submitting a succinct ZKP proof, this pi here, that is sent on layer 1. And on layer 1, we are verifying this proof. So just a bit of more details of what is happening here. Here we give an example of the scroll layer 2 rollup. And essentially, this slide contains the same information as the previous one, but a bit more detail. So this here is the Merkle-Patricia tree reflecting the current state of the L1 chain with its own current root. And then we have transaction or a list of transactions that we want to execute. Now, if you just focus on the upper side, here we have whatever happens on L1, so no ZKP for the moment. And what will happen is the transactions go into the Ethereum virtual machine. They're executed by the executor who is pushing, popping on the stack and reading and writing on the memory, so this is transient memory. He also has access to some list of published smart contracts in the form of bytecode and some memory storage. As a result, the transactions are executed on L1. Okay, so in this transaction or list of transactions are internally represented as bytecode, so as this kind of an execution trace. Now we introduce the ZKP component. So on layer 1, instead of EVM, we have a ZK EVM. So this is an EVM equivalent. So I have O here because it implements all EVM codes modulo sum. So we have degrees of equivalence. But regardless, the ZK EVM can compute anything that the EVM can. And as an input, it takes in the list of transactions that we want to execute on layer 1, the current state root of the world state, and it outputs a succinct proof pi. And this proof pi proves two things. One is that the execution tray is unique and it is valid. Valid meaning it follows the rules of the EVM, so the correct opcodes that achieve the correct computations. And the second thing is that executing this execution trace causes a valid transition to the new state root. So we will move from this state to a next state, T+1. Illustrating an application on private transactions. So how do we address privacy with ZKP? Now, a naive approach would be to work with encrypted accounts. But this turns out to be infeasible in practice. So A and B want to send a transaction between each other, then they have to encrypt their accounts and decrypt them on each side. So it requires a lot of interaction and it is not feasible and it's expensive. So an example of a successful project that is using ZKP for addressing privacy is Aztec network. So they are privacy-first ZK rollup on Ethereum, and their core idea is that instead of working with accounts and balances, they're working with nodes and owners. So nodes as in bank nodes, and then all the funds of the chain are represented by a huge set of nodes, and every node has a label, and this label is its owner. So when you do a transaction, it simply comes down to relabeling the corresponding nodes. This makes the setting much simpler if we want to achieve ZKP. So in Aztec case, they maintain all the nodes and their owners in encrypted form in a Merkle tree, and they have a second Merkle tree that keeps track of the destroyed nodes. Because of the UTXO model that they use, or similar one, you need also to keep track of what kind of nodes were destroyed. So to make the long story short, within this setting, you can prove statements in ZKP that have the following form. So the Merkle tree M contains a node of value X that is owned by Y, which does not have a nullifier in N, meaning it does not have a corresponding node in the tree of destroyed nodes. So that's a valid node. So we've seen how we can use ZKPs to address privacy and scalability. And here I move to the second part of my talk, which is about vulnerabilities. So as useful as they may be, thank you, as useful as they may be, ZKPs have introduced a whole new class of vulnerabilities. And in the past years, 5 or 10 even, we've been slowly accumulating knowledge in different ZKP vulnerabilities that appear in audits. And only recently, in 2024, a paper was published that systematized all this knowledge by Chaliasus et al. It systematized all this knowledge and broke down all different vulnerabilities that we have seen so far into classes and into kind of properties that it is breaking. So in particular, they analyzed 141 ZKP vulnerabilities that are publicly available. They broke them down in classes, and here is a very brief summary. So in terms of the core properties of ZKP that they're breaking. So we can break soundness by bugs in the circuits, specifically under constraint circuits and arithmetic field errors. We can break soundness in improper Fiat-Shamir application or into the backend more generally, where you implement the prover, the verifier, or the setup. And for completeness, you can still have bugs in the circuit, handling the point and infinity, we'll see in a moment, and backend as well. And for zero knowledge, blinding is a common error. You can do blinding wrongly. We can see again in a moment, and then processing private inputs as public data. One thing I want to say on this slide, breaking soundness is the most critical vulnerability that you have. So breaking soundness allows you to forge proofs and steal funds from the network. So this is by far the most serious bug that one may have in his implementations. Completeness and zero knowledge can be bad, but not as bad. Okay, so highlighting very quickly 3 vulnerabilities found in our audits that break each of those 3 properties. So one vulnerability is a break on soundness that we found while auditing the linear Plonk verifier. So what you see here is the vulnerable part of the code, and more specifically, this is the last round of the Plonk verifier, in which the verifier is generating a challenge. If you remember the Fiat-Shamir in the beginning of my talk, the verifier is generating challenges that are supposed to be pseudo-random by following the Fiat-Shamir transform. Now, in this particular case, the developers did not include all the public information into the Fiat-Shamir transform. They figured, since this is the last challenge, it's sufficient for it to be pseudo-random, but we don't have to necessarily include all the previous messages into its pre-image. That saved them a bit of efficiency, but it turned out it caused a serious attack. So I won't discuss too much this slide, but it all comes down to essentially being able to freely modify some elements of the proof. Thank you. Some elements of the proof without modifying the challenge, and as a result you end up with a simple system of 2 linear equations in 2 unknowns, which you solve for x and y. You replace x and y in a forged proof, and this forged proof will be accepted as valid. And what are the implications? Well, on layer 2, an attacker makes a false transaction that transfers all the user funds into an attacker-controlled account. He builds the Merkle tree, he constructs his new Merkle root, he makes his forged proof pi prime that will cause correct transition from this root to the old one, and because of the bug, this false proof will be accepted on layer 1, and then the chain correctly transitions to this new state in which all the funds are into the attacker account. Okay, very quickly, a bug on breaking completeness. It's we've seen, so this is not from one particular audit, but we've seen it at different places. How do you handle the point at infinity on an elliptic curve? So it's a point that has coordinate 0, 0, and it's the only valid point on the curve that does not satisfy the curve equation. And many implementations just choose to ignore this point. So if you get a commitment equal to the point of infinity, you just ignore it. That's fine, but if you have a polynomial that has a commitment, that has roots in the secret parameter s of the SRS, then its valid commitment will be the point at infinity, and you will be ignoring this point. So as a result, you break completeness. So valid proofs will be rejected. And finally, a bug on zero knowledge. So a certain implementation, specifically the linear Plonk prover implementation, did not properly blind their polynomial. So you are seeing here the 3rd round of the Plonk prover, in which at some point you are computing, well, not at some point, but that's the main goal of the 3rd round, you're computing this large quotient polynomial, and it's broken into 3 sub-polynomials, which you're supposed to blind. So what does it mean blinding? It means adding those random factors to the original polynomial. So this row 1, row 2, and so on. Adding blinding is, the idea is to prevent leaking of witness data by publishing commitments to those polynomials. And in this implementation, this blinding was not done. So the polynomials were just published as is. Okay, and as a result, it directly makes applicable an attack recently proposed by Sefranek that actually addresses exactly this case. So it breaks statistical zero knowledge in zero knowledge proofs. That's my final slide. I want to end up with some wrap up. So the main message is that ZKP auditing is a challenging field. Now it's fast moving. We see new protocols being proposed every month, if not every week, and we don't have an established checklist. So at this stage in time, it's very different than smart contract auditing, for example, where we have established checklist of bugs we want to track. Many of those can be automated, and so on. We don't have that yet for zero knowledge. Often auditing requires specialized knowledge in cryptography, so the bar to enter can be high, not always. If you audit circuits, it might be a bit easier. And then we have also limited tooling, so we don't have the comfort of fuzzers and automated bug trackers, although we have some tools, but not many. So finally, for guidelines, if you are a ZKP auditor, pay special attention to custom modification of a protocol. So you will be auditing a protocol that follows some paper. If you see a component that is modified from the paper, now that's a red flag. Be careful to audit this carefully. Also be cautious with recently proposed schemes. It's an abundance of them. As I said, new papers are being proposed every month. If you are an implementer, follow the paper. So make sure you're using the latest version and maintain detailed specifications as you do the implementation. Read audit reports. There are many reputable auditing companies that do excellent work and they publish their reports, so reading them is very informative. And finally, consult a cryptographer or an auditing company if you're building a complex project that has critical ZKP components. So thank you very much.